So this video is about complex circuits. So far dealt with just simple series and simple parallel circuits separately. Now we're kind of deal with them together. So you can see on the right, we've got this really complex circuit with a processor and all these other different components, which we could get into, but we're not going to. We're going to keep things kind of simple for this class. But we do want to look at what happens when you combine those pathways of series and parallel together. So on the left here, we can see our two simple circuits that we built. We've got series circuits, we've got a simple parallel circuit with two light bulbs each. Then on the right, you have this complex circuit, and all of these brown things that are inside here, those are all different types of resistors. So you can see there's lots and lots and lots of resistors that are within the components of some electronics. And we would need to figure out the relationship between them because that's going to help us figure out the current and the voltage everywhere, which is really the driving force behind everything in a circuit is how much current's flowing through it and what voltage is at that particular point, because that's what's going to determine how something functions. So here again, we have another simple circuit, or in schematic form now, with our battery switch light bulb, nice and easy. But then we have this is a transistor intercom circuit, which has all sorts of different components. Some we're not going to deal with at all, some capacitors and some other things like that. We're going to worry about that, but you can see that we have resistors in all sorts of different locations in here that are doing different tasks than they would in just a simple series or a simple parallel circuit. So let's figure out how we could break down maybe a circuit like this one, but one that involves both series and parallel resistors simultaneously. So it comes down to starting off with simplifying. So we need to simplify something like this into its equivalent resistance. That'd be our first goal, meaning what one resistor could we replace everything in this circuit with that's going to have the same effect on our battery. So the first thing I want to do is add any resistors in series. So that's not too hard for this one. There's actually only two resistors in series, the 2 ohm and the 4 ohm resistor, okay? Because those are the only two that every single electron has to go through, or any point where if some electron or charge goes through one resistor, it's going to have to go through the next one. All the other ones have options and choices. They don't have to do both or three, so we can just these are the only two that are in series, so we can add both these two together. And 2 and 4 means we could replace both of these two resistors with a single 6 ohm resistor. Okay, so that's our first step towards simplification. Not too hard there. Now we need to simplify resistors in parallel. So that's our next goal, is simplify those things. So what do we have that's in parallel? Well, we have this 3 ohm resistor here, but it's in parallel. So here's one path. It's in parallel with everything over there. So we can't deal with all three of these resistors right now. So we need to simplify these three down. So the first step would be to simplify our 6 and our 12. So we know that 1 over r is 1 over 6 plus 1 over 12, okay, which means that 1 over r is 3 over 12, which means that R is 4 ohms. What does that mean again? Well, that means instead of these two, we could put in a single 4 ohm resistor here. And now these two are actually not, we've simplified them out of the circuit. Now, granted, they are still part of the real circuit, but in terms of figuring out RT, they are now out of the circuit. Now, hopefully you guys can see this, remember that. And we now have a 4 ohm resistor here and a 2 ohm resistor here that are in series. So those become easy to deal with. Those become a single 6 ohm resistor. So now we've replaced everything over here. This is now gone with that single 6 ohm resistor. Okay? And now we've set ourselves up for some success here because we have, hopefully you see we have two pathways. We have a 3 ohm resistor pathway and a 6 ohm resistor pathway. So 1 over R is 1 over 3 plus 1 over 6. And if we solve that out, this is 1 over R is 3 over 6, which means that R is 2 ohms. So what that means is, again, we could replace everything over there with a single 2 ohm resistor. So now everything to the right has been removed, simplified out. Now, granted, it's still there as part of the circuit, but in terms of figuring out total resistance, it's now gone. And now that we have those resistors simplified, our next step is just, well, add the resistors that are in series, because right now that's what we have left. We have a 6 ohm resistor and we have a 2 ohm resistor that are in series. So we add those together. We get RT would be 6 ohms plus 2 ohms. So RT is going to equal 8 ohms. Again, what does that mean? Well, that means if we put this same 8-volt battery here and an 8 ohm resistor, we're going to get the same amount of current out of that battery as we would with all of those resistors over here. So I'm going to get rid of a lot of these scratch outs just because, again, those circuits are really there. We just kind of simplified them down, but that way you remember that that actually is the real circuit, and these components here represent portions of the circuit. Okay, so now we got RT. Again, that helps us. We remember from our other circuits, RT is going to help us find the total current leaving the battery. So IT again is VT over RT, which in this one is nice and easy. We have a total of 8 volts. We said we simplified everything down to 8 ohms. So that means we have 1 amp of current flowing out of the battery. So 1 amp of current making its way out of the circuit. Now again, at points here, at this point, that current's going to split, right? Some of it's going to go that way and some of it's going to go that way. We'll figure that out in a little bit. And also at this point here, some of this current here, so that top current is going to go this way and some of it's going to go that way. Okay. And again, they meet back together here and here at this point. And then the overall current is going to meet right here. So back here, if we measure the current, we'd be back up to 1 amp. So we know the total current leaving the battery. Then we need to figure out the splits that are going each way. Again, that's important because that's going to regulate power across each resistor, right? Since power equals current times voltage. If I know the current that goes each direction and I know the voltage that goes through each resistor, I'm know how much power I'm using at that resistor. And this will be really important for understanding like what devices we could use in a circuit. So now that we've got all that worked out, we know that IT is 1 amp. Again, I'm going to put some of these back in here now. So we had that imaginary resistor we put here that represent everything out to the right. We had that single 4 ohm resistor here that represented the 6 and the 12 ohm resistance. Okay, and then we have this right here, and then we also had the 4 and the 2 added together to generate that 6 ohm resistor here that represented the 612 and the 2. So that's great. Now we need to figure out voltage drops. That's going to be our next key. Because again, when we think about parallel circuits, remember for parallel, V is constant, right? The voltage drop is constant across each path. And again, for series, again, quick reminder, current is constant. Make that actually a C. There we go. So let's figure out what those voltage drops all are at each of the individual points and see how we're going to use that to determine some different things. So what we want to do first is we can just go 1 amp through this 2 ohm resistor. Okay, cool. We're going to drop 2 volts there. We know V equals IR. We also have 1 amp going through this 4 ohm resistor because it's in series. So we know we're going to drop 4 volts at that resistor. Okay, so those are 2 keys, 2 pretty easy steps. Now the question becomes, how do we deal with everything out to the right? So here's what we're going to do. This setup right here, we go from this point to this point, right? From the top to the bottom. If we go down or if we go to the right, we have to lose the same voltage as we complete that loop as if we complete any loop going over here, right? So because of that, let me get rid of these lines so we don't get too jumbled up. Because of that, we need to find what is the voltage difference here. Okay, how much voltage am I going to drop from one point of that parallel branch to the next? Here's how we're going to do it. it's not going to be the 8 volts of the battery because we've lost 2 volts here. We've lost 4 volts here. Okay. Now, if you do a quick subtraction, you realize, oh, hey, it's 2 volts left. Yeah, that's right. Good. But the more appropriate way to do it is thinking about the fact that we turned all of those 4 resistors into that single 2 ohm resistor in series. So if we did that, we have 1 amp of current going through that imaginary 2 ohm resistor. And what would the voltage drop be? Well, we would lose 2 volts at that resistor. That means when we go through this whole pathway, we are going to have a voltage drop of 2 volts. Okay, so driving current straight down and driving current to the right through that mix of stuff over there is going to be a 2 volt energy, electropotential energy that's going to drive things through that circuit. So that is going to help us figure a bunch of things out eventually. Okay, let's help us figure out the current for each direction. Okay. So you might think, okay, that's cool. How do we do this one? Well, that one we're going to wait on for a second because we know that between here and here, so if we go between this point and this point, we have to lose those 2 volts. I'm going to get rid of some of these squiggles, sorry. We have to lose that 2 volts worth of energy, but we do have a series resistor in there and the parallel branches, so let's hold off on exactly how that's going to work yet. Okay, we'll get to that voltage difference in a second. So as of right now, I'm going to erase this. We know that we drop 2 volts at this 2 ohm resistor here. Up here, we're going to drop 4 volts at this resistor right here. And this 3 ohm resistor is going to drop 2 volts worth of energy. Okay. Now, where's the other 2 volts though if we have this separate pathway? Well, we turned all 3, this resistor, and this resistor over here, into that single 6 ohm resistor. So across this imaginary 6 ohm resistor right here that we're representing everything with, we're also going to drop 2 volts worth of energy. Okay. I'm thinking, okay, how's that going to help me eventually? Well, we'll get there in a second. So now we've got the voltage drops across the first resistor, the first resistor that's in series, second resistor in series, and our parallel branches. Our next goal is to figure out the current in parallel. So we know we have 1 amp of current going into here. We know we're going to have a 2 volt drop between the 2 sides. So now the question becomes how much current goes this way and how much current goes that way. Well, again, just a quick reminder, we did turn everything over there into that 6 ohm resistor, and everything over here is that 4 ohm resistor. So let's figure out I. So we know parallel branches, I equals V over R. And V, again, for going straight down is 2 volts. And R for going straight down is 3 ohms. So, well, we have 2/3 of an amp of current that goes in that direction. Okay, not too bad. Now the question becomes, how much is going to go? So that's 2/3 this way. We can do a quick subtraction and say, okay, yeah, we know it's going to be 1/3 because there's a total of 1 amp. Great, fine. But say there's like 20 pathways and we need to know how much current goes each way. And they're all different resistances. Well, that subtraction isn't always going to be easy. So let's go off mathematically solving it. So we know I is V over R again. And we know we have a 2 volt drop. Thing is, we have a 2 volt drop across everything over here, but we turned everything over there into that 6 ohm resistor. So we're dropping 2 volts over a 6 ohm resistor, which is going to give us our 1/3 amp of current. So now that we know there's a 1/3 amp of current going that way, okay, that's actually going to let us find the voltage difference across this parallel circuit over here. Because remember, we turned the 6 and the 12 we turn the 6 and the 12 into that 4 ohm resistor. If we have, again, there's 1/3 of an amp going into this split, and if these two aren't here, and we just have that 4 ohm resistor, we have 1/3 of an amp going through a 4 ohm resistor. So that means the voltage drop from this point to this point is going to be 4/3 of a volt. Okay, which means that if we get rid of this, we're going to drop 4/3 of a volt here, and we're also going to drop 4/3 of a volt there. Since we also know 1/3 of an amp is going through this 2 ohm resistor, we have 1/3 of an amp times 2 ohms. We know that 2/3 of a volt is going to be dropped here. And the 2/3 and the 4/3 add up to the 2 volts. So 4/3 plus 2/3, of course, adds up to 6/3 of a volt, which is the exact same as 2 volts, which is how much energy we need to lose on that parallel circuit. So now we know the voltage drops at each of those two pathways. We know the voltage drop across each pathway is 4/3 of a volt. The question just becomes, how much of my current goes in that direction? So now that we have, I'll erase some of this here, so I have some more room to work with. So now that we have 4/3 of a volt across a 12 ohm resistor and 4/3 across a 6 ohm resistor, we can actually find I for each pathway. I don't know why the eraser's not working so well. There we go. Okay, so I equals 4/3 divided by 6, and I equals 4/3 of a volt divided by 12 ohms. Okay, so 4/3 divided by 6 is 4/18 amps, and 4/3 over 12 is 4/36 amps, and that would be 12. If I add those two together, if I do 4/36 plus 8/36, add the individual currents, we get our 12/36 of an amp, which is 1/3, which checks with what came in to that parallel branch. So I realize it seems kind of complicated, but it's all piecemeal. Take it step by step, go through each thing, think about what's in series, think about. So it seems like a lot, it can seem pretty daunting, but if you take your time and you understand all the basic properties of the things we've been dealing with the whole time and realize that all of those are just going to dictate what you're doing, you're gonna be fine. So again, steps to kind of follow: simplify all the resistors in series, simplify all the resistors in parallel, then simplify all the resistors to their equivalent resistance. So that's the initial part, finding RT. Then find the total current for the circuit, then use that to find the voltage drop across all the equivalent resistors. That's where you're using those resistors that represented like parallel branches. Find the voltage drop across all of those. Then you can use that voltage drop to find the current that goes through each pathway, and then you can use that in the end to find the voltage drop across each of the resistors that are in series on the branches. You might ask, like, why would we do this? Why would we have something set up where there's a resistor and another resistor here, and on the other side there's only a single resistor in a parallel circuit like this? So again, what do resistors do? Well, resistors take energy to get through, right? They're using up some of the electric potential energy. They're using up some of that voltage. So if you come in with 12 volts here, on one side, you're going to use 12 volts. But here, you're going to split it up. Maybe you use 6 and maybe you use 6 if they're both the same. Well, if this one and this one are both light bulbs, one will be brighter, one will be dimmer. Or if they're motors, one will spin faster, one will spin slower. or whatever kind of operation or function they're doing, you're going to regulate that amount of voltage that it's getting. Okay. So the idea of having things in series and parallel is so that way you can regulate things. Series resistors are great for regulating voltage. They're not great for lots of other things, but they're great for regulating how much energy is actually getting to a certain point, which is why you need them, why you need those resistors in series. They're going to take something like a 12-volt power source, but if your battery on one path your light bulb on one path can't handle more than 6 volts, well, you put a resistor in front, and that allows for that bulb to work. So hopefully this made sense, and the worksheets that go with it make sense too. Come with questions, come ready to ask, and we'll kind of go through a bunch of practice of this. Make sure you guys kind of get all the tricks and see all the patterns and work through kind of the puzzle of the whole thing.